Today, we're going to talk about the derivative. This is the big Calc 1 topic that we talk about. We'll be pretty much talking about this for most of the rest of the semester. This is really what we're using all of the stuff that we've done so far to build up to. But first, we're going to start talking about the difference quotient. You might recognize this here. You've probably done some things in algebra with this. I just first want to remind us what this actually is. So here I've just drawn some function f, and what I want to do is plot some points on here, and we'll see what's going on. So let's first just plot a point right here. We'll call this x, and we know then that the y value here is f of x. And we're going to plot another point on here, but instead of calling it like x2 or something like that, what we're going to do is we're going to define the second point on this graph kind of in relation to this first one. So I'm going to put it over here for now, but instead of calling this something else like x2, I'm going to define this based on the identity of x. This is kind of like if you have an older sibling, maybe you'll relate to this. I'll shorten this story up. I'll try to be quick, but I've got an older brother. He's about 1.5 years older than me, and we were really close friends growing up. All that stuff was great. But when he went to high school, we were kind of separate for a little while. We went to different schools. When I then went to high school, I went to the same school as him, and he'd already been there for a little while. So on the first day of classes, when all the teachers were going through the roster and all that kind of stuff, they got to my name, and they asked me the same question in every class. They asked me, "Are you Tim Keep's little brother?" Because he'd already built this identity, I was just related to him based on my relationship to him. So instead of being, Peter Keep, what he was just the little brother of Tim. We're going to do that to this point. We're not going to call this x2. We're going to call it x plus h, where h is just going to be, I'll try and make this a bit bigger. Here we go. H is just going to be this distance here in between the 2 points. So we're just solely focused on how these two things are related. So like if this x value was -1 and this one was 4, we'd really say this was -1 plus 5. We're really focusing on the relationship between these two. Anyways, once we've got this x value, we also have a y value that goes with it, and it'll be f of x plus h, whatever that is. And what you'll notice is that this difference quotient here is a difference in y values over h, which is the difference in x values. What we've really got here is the slope of this line in between them. That's what our difference quotient finds. It finds the slope of a line between 2 points, where h is the space in between the 2 points on the x-axis. So this seems like a bit of a weird way of doing things. Normally, we'd say something like, oops, I got to get off my straight line. Normally, we'd say something like m equals y2 minus y1 over x2 minus x1. It's the exact same thing going on here. We're just stating it all a little bit differently. We're focusing more on this h relationship between them. That's going to be important for us because what we're going to do is we're going to use some limits, and we're going to make this h distance get really, really small. I want to show you something that I've got up on Canvas, so you can take a look at this if you'd like. You can click this little drop-down menu over here to change the type of function that we're going to look at. I'm going to just look at the cubic one because that's going to be kind of similar to what I had. So here, you'll notice I've got my x value. It's a little hard for you guys to see, but I started at -1. That's where this point is. And h is like 2 2/3 approximately. So here's my point. But what we can do now is we can drag that h value and make it smaller. And what you'll notice is that our red point gets closer and closer and closer to the black point until the slope that we're finding is actually more like the slope of a tangent line instead of a secant line. A secant line is like a line going between 2 points, like something here. A tangent line is a line that just touches 1 point. So here you can see the slope is -0.75, As we bring this point closer and closer, the slope changes. Now it's at -1.5, and it looks like it's getting kind of smaller and smaller and smaller, or I guess I should say bigger, closer to 0. That's a little weird with negative values. We're looking at -1.36, for instance. We can change the x value that we start out. We can change the side that we look at. We can make h negative, and now we're looking at what happens on the left. Over here, we've got some slope of around 1/2, and as we bring it closer, the line changes, and we start looking at a tangent line instead. And you'll notice it looks like it's getting close to the same value here, around -1.3 something. I don't know. We could figure that out later on. But what we're going to do is we're going to make h get really, really small. So let's go back to this. And what we're going to notice is that when we make h really, really small, all we're going to do is put a little limit statement out in front of here. We're going to focus on the limit of this thing as h goes to 0. That's going to take this red point, drag it closer and closer to this point that we've picked, and it's going to look at the slope of a tangent line instead. Let's go ahead and do that numerically first. Let's try and estimate the slope of the tangent line when x is equal to 2 for this function. So what I'm going to do is I'm just going to find a couple of different slopes. I'm going to go and I'm going to look at the interval between 2 and 3 to start. This is not going to be a very good estimation of the slope of the tangent line, but let's just see what we've got. We'll say our slope then is going to be f of 2 minus f of 3. Actually, you know what? It's normal to put them in the other order, so I'll just do that. That way we don't get confused when we look at our textbook and see it in the other order, although it doesn't really matter. So I'll put 3 into this thing, and I get 3 squared, which is 9, plus 1, that's going to be 10, minus 2 squared is 4, plus 1 is 5, over 3 minus 2, that's 1. This gives me a slope of 5. So there's one estimation. Let's go ahead and mark this off, and we'll do another one. Let's look at maybe the estimation between of the slope between like 2 and, let's get close. Let's call this 2.1 here. I'll probably need to bring up my calculator in a second to find some of these values, because now I'll plug 2.1 into this thing. I'll plug 2 into there, and I'll look at 2.1 minus 2. Some of these I already know. I already know f of 2. It's 5. So I'm going to have something minus 5 over 0.1. So if I plug 2.1 into my function, I get 2.1 squared, which is 4.41. And then when I add 1, I get 5.41. So when I subtract these things, I get 0.41 over 0.1, which gives me 4.1. That's a better approximation of the slope of my tangent line. Now, I could do this more times. I'm not actually going to do it all the way, but I'll set it up. I could go ahead and get a little crazy and say, let's look at the interval between 2 and 2.001. And so I could say my slope now is f of 2.001 minus f of 2 over 2.001 minus 2. And I could plug all this stuff in, get some value, and it would be a better approximation of the slope of my tangent line. Notice all that I'm doing, though, is I'm making these 2 points, these 2 x values, get close to each other. If I call this starting point 2 and the second point 2 plus h, then what I've got is over here, h is 1. Over here, h was equal to 0.1, and over here, h was equal to 0.001. So in each of these, I'm just making h get successively smaller, closer to 0. That's a numerical approximation of a limit. So what we want to do is just actually use our limit statements and see what's going on. Here's our definition first before we do anything, though. We've got this limit. This is what we're going to call the derivative. We denote it using this notation here, this little apostrophe-looking tick mark. We call this f prime. That little tick mark is read as prime, and it's literally just means the derivative of the f function. The derivative of f at x, denoted f prime of x, is that limit of the difference quotient. Notice this thing here if the limit exists. We'll talk about that a little later. We'll talk about what happens when that limit doesn't exist. If the derivative does exist for x at a point or on an interval, we say that f is differentiable, just like we could say that f is continuous at a point or continuous on an interval. We'll say that if the derivative exists, it's differentiable at a point or on an interval. There's a couple of interpretations. We'll build these up as we go. But the first thing is that it's the slope of the line tangent, just like we saw in that little picture visual demonstration-y type thing. Since slope is a rate of change, though, we could say that the slope of a secant line between 2 points is like an average rate of change, and so the slope of the tangent line is an instantaneous rate of change. So anytime we talk about slopes of tangent lines or we talk about instantaneous rates of change, we're going to be talking about this derivative. We're talking about how our function is changing right at this particular moment. Here's like a physical application. The derivative of position, if you had some function that defines the position or height or something like that of an object as it's moving, then the derivative is the rate of change of that, which is the velocity. So we could figure out exactly what the velocity of an object is. And if we had a function that defined velocity, then we could say the rate of change of velocity is acceleration. And so the derivative of velocity is the acceleration of it. We'll add more interpretations, but they're still going to be just based on these two, talking about rates of change, talking about slopes of tangent lines. Let's just get into it a little bit. We'll see if we can do some algebra, do some limit stuff. So we're going to say f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. This definition, this difference quotient, will get figured out if we practice this pretty well. Whenever we're looking at f of x plus h, that's literally just taking x and putting x plus h into there. So we're going to have a limit as h goes to 0 of 1 over x plus h minus 1 over x over h. Here's our x plus h function. There's our regular function. So we can say this matches up with that. This matches up with that. At this point, we'll notice that if you plug 0 in for h, you get 1 over x minus 1 over x, which is 0, over h, which we said was 0. You're going to get 0 over 0, that indeterminate form, which, if you remember, means that we have to do algebra. And so far what we've seen is that we can factor things and do stuff like that. The algebra that we're going to do here is going to be a little bit different. We're going to go ahead and add the fractions on the top together by using a common denominator. I'm going to multiply this first fraction by the denominator x over x. So I'm going to have x over x times x plus h minus x plus h over x times x plus h. I'm just multiplying both of these fractions by the opposite denominator, just like we would do in a regular fraction setup if we were subtracting fractions with regular numbers. Now we can go ahead and subtract things. Make sure that we use the distributive property with this negative sign. This is really x minus h again. So what we're going to have is the limit as h goes to 0 of negative h over x times x plus h over h. This is kind of an ugly looking thing. So what I'm going to do is rewrite this fraction. Whenever we divide, that's the same as multiplying by the reciprocal. Dividing by 2 is the same thing as multiplying by a half. Dividing by 3 is the same thing as multiplying by a third. So I'm going to say this is really the limit as h goes to 0 of negative h over x times x plus h times 1 over h. And now we can see pretty easily that these things cancel out. We still have a negative sign here. So I'll move all this up here. We've got this limit still as h goes to 0 of negative 1 over x times x plus h. And now we can plug 0 in. Now we get negative 1 over x times x. That's negative 1 over x squared. That's not really what we're used to seeing as an answer for a limit, but what we'll notice is that h was the thing going to 0, and so we're still left with x's. This is a derivative function. This thing will tell us slopes of tangent lines and things like that for our function 1 over x. So when we have fractions like this, go ahead and just combine those using common denominators. Let's take a look at another one before we get into like applications of this thing. So here we've got our square root of x thing. We'll go back and we'll say, all right, f prime of x is going to be this limit still as h goes to 0 of f of x plus h minus f of x all over h. Now, when we plug in x plus h into our function, we get the square root of x plus h minus the square root of x all over h. Here, we're a bit stuck because we can't subtract these things. When we had 1 over x plus h minus 1 over x, we just could say, oh, we can subtract fractions using common denominators. Here, we can't do that with square roots. There's a lot of work that you could do to find this trick, but essentially we're going to have like a trick that we pull out of a hat. We're going to multiply by the conjugate. So we're going to use the conjugate. What that's going to look like is this. You might remember the conjugate. We've used this before. We use it a lot when we're dealing with complex numbers. We're just switching the sign here. Make sure that we do the distributive property on all this stuff. What you'll notice is that if you do the distributive property now, you get the square root of x plus h times the square root of x plus h. That's just going to be x plus h. Then you're going to have the square root of x plus h times the square root of x. So I'll just write that out. I don't know what that is, but we'll see. Then we're going to have negative root x times root x plus h. Notice that these two are the same thing added and subtracted. So they're just going to add up to get 0. I'll cross that whole thing out. So it really doesn't actually matter what those things are. Then we've got negative root x times root x. That's going to be minus x. And that's all over, I'm not going to multiply this out. I'm just going to write it as h times the square root of x plus h plus the square root of x. I'm not going to do the distributive property here. All right, so now these things are gone. Maybe I'll just scratch them out fully so they don't distract us. Notice that we also have x minus x. Those things are going to be gone. We're just left with h. So let me write it out one more time. Limit as h goes to 0 of h over h times these two square roots added together. But now you can see we've got these nice factors that we can cancel out. So we're really left with the limit of 1 over all this stuff. If we make h go to 0, what we're going to have is 1 over the square root of x plus the square root of x, which is really 1 over 2 root x. That's the derivative f prime of x. There we go. So in both of these, we've got some algebra tricks. These are going to be the two types of like hard instances for our derivative. So the two algebra tricks, again, are adding these things up by using common denominators here when you have fractions. And when you have square roots, we'll use this conjugate trick. So those are going to be our two hard things. Let's take a look at actually finding the slope of that tangent line that we were estimating earlier. I think we had like 4.1 was our approximation, and we could have got a better one, but oh well. Let's see if we can estimate this now. So we're going to find our derivative function, and then we're going to remember that the derivative is really the slope of the tangent line. We're given an x value, so what I'm going to do is first find f prime of x, and then second, I'm going to find f prime of 2 by just plugging 2 into my derivative function. Since we're left with x's when we do our derivative, we can evaluate that function at points, and then we'll get the slope of our tangent line there. So that's the general idea of kind of what we're going for here. So let's first find f prime of x. So we'll say f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. We'll plug in our x plus h here. That's going to give us x plus h squared plus 1. Ooh, that's a brutal x. Let me fix that. That's a bit better. So instead of x squared, we're going to have x plus h squared. So we've got a limit still as h goes to 0 of x plus h squared plus 1 minus our whole function x squared plus 1. Notice that the 1's are going to add together or subtract, I guess, to get 0. 1 minus 1. So that's going to go away. But let's first figure out what this x plus h squared is. Oh, and all this stuff is over h. So if you multiply x plus h squared by just doing x plus h times x plus h and use the distributive property, you're going to get x squared plus 2xh plus h squared plus 1. That is f of x plus h. Then we can say minus x squared minus 1. That's subtracting off our f of x. Now again, you'll notice the signs are changed, but that's because we're subtracting it. All that stuff is going to be over h. So now we'll notice a bunch of stuff's going to cancel out. X squared minus x squared goes to 0. 1 minus 1 goes to 0. So we're really just going to be left with the limit as h goes to 0 of 2xh plus h squared over h. Notice that we can pull out a common factor of h. That's going to be h times 2x plus h over h. And now those h's can cancel out. So we're really just left with the limit as h goes to 0 of 2x plus h, which if we put in 0 for h, we've got 2x plus 0, which is just 2x. That's f prime of x. Now, if we want to find the slope of the tangent line, we can find f prime of 2. So let's go ahead and bring this thing over here, and we'll say f prime of 2 is going to be 2 times 2, that's 4. The slope of our line tangent to this parabola, x squared plus 1, is 4, which if we went back and looked at our approximation, we found we were getting 4.1, which is close. And if we had done more and more of these things, we might get like 4.01 and 4.001 and things like that. We could guess that it's actually approaching 4. We can go further than that. If we can find the slope of the tangent line, then we can find the actual equation of the tangent line here. So let's go ahead and do that. First, we know that slope is derivative. So that means that m in this case was f prime of 2, because that's still our x value, which we said was 4. For the equation of a line, we need the slope, and we also need a point on the line. What we're going to notice, though, is that we have a point. If I just draw this parabola function, and it's going to be kind of bad, but oh well. Let's say this is our parabola, x squared plus 1, and we want to look at the tangent line when x is 2. So let's say here's the point that we're looking at when x is 2, and we're going to look at our tangent line. It's going to look something like that. We know this line, that's not great, but oh well, has a slope of 4, and we also have this blue point on the line. But notice that that's also a point on this graph. We know that the x value here is 2, and the y value can just come from our function, f of 2. So here we've got that x is 2 and y is f of 2. Essentially, we can say that the derivative gives us the slope, and our original function spits out y values. So if we plug 2 into here, we get 2 squared plus 1. That's going to be 5. Slope, x value, y value. Now, we can either do point-slope form, which looks like this, Sometimes the notation is a little bit different, but I'm a point slope guy. This is what I like to use. So I'd say something like 4 times x minus 2 plus 5, and then I'd multiply all this stuff out, and I'd get 4x minus 8 plus 5. That's going to be 4x minus 3. Cool. Or, if you want, we could be y equals mx plus b people. Some of you guys will be y equals mx plus b people, and we'll just plug everything in and solve for b. So we're going to say 5 equals 4 times 2 plus b. 5 equals 8 plus b. Oops. There we go. And so here, if we subtract 8 from both sides, we get b equals negative 3. So y equals 4x minus 3. In either case, you get the same tangent line. That's the equation of this blue tangent line that we've got here. So we can use this derivative to do some cool stuff. That's pretty much how things are going to go for this. Give some of these things a shot. And next time what we'll look at is trying to sneak through some of the limit work, some of this work here, by finding some patterns and things like that.